We shall start, I think. As you can see, today's lecture will be about image processing and analysis. We will try to analyze some IFM data with Gwyddion, and I hope you all installed Gwyddion on your computers, because today we need to mix somehow a lecture with /seminar with /practice. So today we will cover such topics as I explain you what is a data type of IFM. Also, I explain you how to do image processing, starting from corrections. We discuss on main corrections that we need to do before treating any image in IFM. And then we start doing some kind of like practice related to how to open files, how to import them, how to treat them, how to get information out of that files, and so on and so on. So Gwyddion is a modular free software that helps you to proceed, analyze, correct, visualize any XYZ data. This is very important because you need three rows in your file to get visualized in Gwyddion. So it can be IFM data, it can be data from any of your practical work, scientific work, even if you wanna, for example, make some geographic mapping. So you need kind of like coordinates, and you need the data that you wanna visualize. So again, X, Y, Z. And then you create image, the flat image like 2D or 3D image as well. And usually, as I said, Gwyddion has three columns with the following: X coordinate, Y coordinate, and Z coordinate. And again, Z coordinate, usually X and Y, it's space coordinate, so it's like X and Y. And Z can be anything: volts, nanometers, deflection of the signal, whatsoever. You really can do anything with that. Unfortunately, many companies with our IFM microscope that is installed, we have just TXT file with these three coordinates, but usually many companies, they have their own files where they store all the information they needed, like what is the device name, what is the serial number, and so on and so on. So you just need to find these three coordinates in any file and then export them. Or sometimes Gwyddion can open some of these proprietary file formats or import from these file formats to Gwyddion. Okay, so you just need to type, like in Baidu or Google or Yandex, like Gwyddion import this type of files. For example, it could be MDT if we are talking about MDT. It could be STP, XML, and so on and so on. So there are many of them. The main disadvantage, I think, of IFM, but it's also an advantage, that researcher should really select properly and select only necessary data for treatment and treat it properly. And then process this data to get the image. And this part is on you, not on the machine. So don't believe any image that you want to see. Just try to think logically, apply all the corrections, and only after that do some conclusions and so on and so on. what can we do with Gwyddion? We can do some basic operations, and if you open the Gwyddion, okay, where it is, it's here. Yeah, you go to, for example, data process. Here we have basic operations, and we have all this list of operations that we can do, okay? We also can calibrate data, correct data. We have many different filters. Now you see that it's kind of like in a gray style, yeah, simply because I haven't loaded data yet. Once I load the data, you will see all these gray turns back to black, and you can press, and then you can do all this, for example, corrections. Also, you can play with some grains. Also, it's suitable for, I mean, grains, you can mark these grains and select and apply some masks for the grains and so on and so on. Also, important part is Smp modes. With Smp modes, also it's important because we are not only doing some just topography, we also want to have some properties. For example, like we can press to the surface and measure some mechanical properties, or by using magnetic tip, we can deflect or vice versa, retract this tip to magnetic surface, and we can probe magnetic properties. And all this stuff we can do with this Gwyddion software. You can see here it's like force orientation, magnetic, also for some tip visualization. All this stuff we can do. What about image processing? There are several main corrections that is obligatory to be done. The main one is the plane correction. So you remember Anastasia should tell you about the piezo elongation and deflection and so on, how it works, right? So then let's assume that this one is our a piezo scanner, and then we elongate it one side and then shorten the other side, so we move it like this, yeah, very precisely this way. So we do not have the plane, yeah, all the time. We can retract like this and like this, okay, but if we want to move here or there, we do it like this. So it's a semisphere or sector, and this we should correct first, usually, and also yeah, okay, it's the second one. The first one is like the sample. So the sample also has some tilt like this or like that, and this tilt may not be visible by an eye, but since we are working at the distances of several atoms, like with a resolution of several angstroms in z direction, of course we will see this this not collinearity, like, so this is level and this is our sample, like this, like this. So this is the first what we should correct. The second one is as I said, piezo movement. This means, again, we have this parabola or semicircle. The second problem is that we need to remove so-called scars or shadowing and properly align different rows, because technically what we do, we move. Okay, I will use my microphone as a sample. We use like this, like this, like this, like this, then move next line, do like this, and we need to align two lines. It's a very stupid word, but align these two lines simply because we might have some displacement caused by temperature changes. 0.1 degree is enough. Because just make your own calculations. For example, if you have steel, not even like silicon steel, and for steel, the thermal coefficient is about 10 minus 5, 10 minus 6. And then you change the temperature not even by 1 degree, but by 0.1 degree. And you still have a change in shape, in form, in elongation, retraction, and so on and so on. So this should be corrected, and hopefully this can be done mathematically, and you will see how it will work. So this is our today's sample. You see there are some lines, like a little bit less, a little bit more, a little bit shifted, but at the end it's nice image, even a bit more sharpened than on the left side. You have the high frequency noise and low frequency noise. And if from high frequency noise you can isolate by simply putting a metallic some metallic cover and so on and so on, low frequency noise is very hard to avoid, and usually you avoid it only when you install the whole setup, the whole microscope on the special tables. And normally this low frequency noise, you cannot do anything with that except improve insulation, noise and vibration insulation. But with high frequency noise, as I said, you can cover, or you can do it again by filter. So this is low pass filter, allows you to cut high frequency noise. And here you see there is like a bit noisy signal, but at the end we kind of like flatten all this stuff by removing these high frequencies. And normally high frequencies is what? Is our voice is also high frequency because it's kilohertz. And when you're working, especially with open IFMs, you will see that even speaking loudly will affect your image, especially in non-contact modes. So in contact modes, it's okay because you're kind of like standing on the sample, but in non-contact modes, you have like all the time oscillating cantilever, and you kind of like bumping on the surface. So if you allow this high frequency noise pass by like loud speaking is enough, you will affect these oscillations, and you will affect resonance frequency. Okay, so now let's do some practice. I hope you will do it with me. So this is a Gwyddion program. I press File, then I go to, okay, let's start with just Open. You see the structure of the file. So there are many different information, like when it was done, what is the data length, history, what is max X, max Y, and so on and so on. So there are a lot of service information, like some even magnifications, whatever, sensitivities, blah 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 blah. You see, there are a lot. And somewhere at the end, so you see, it's even like some parameters were locked, disabled, or whatever. And somewhere at the end, I think data starts here. Wait a second. Right. Yeah, I think the data will start here, but you see it's in codes. encoded. But the same file, open it in Gwyddion, you see all the data decoded. It means that Gwyddion understand what is the file, how to work with that, what to do, and how to turn all these empty squares into numbers and pictures. Okay. Once you select the file, here you have like size in pictures. You have also size in micrometers because we have a lot of information inside of this file. So Gwyddion automatically knows what is the size, what amount of pixels in this picture, and so on and so on. And we have different channels. So the first channel is height. The second one is like so-called peak force error. Actually, sometimes erroring, even there is the whole science itself based on errors in IFM, because it can give you information. Actually, if you know how to treat it properly, it can give you a lot of information on the interfaces between, or boundaries between, different phases, between different materials, and so on and so on. Actually, sometimes people want this force error or phase error instead of regular height or phase. And also here it's in phase, because this is a semi-contact, so we kind of like bumping all the time. This is in phase voltage or phase voltage. So this picture shows how the phase of the signal changes. Also, we can play with these two buttons. The one button and another button, it just changes a bit representation. You see, it's like kind of like pre-treatment done already when you import the file. Okay, we take like this, press open. Okay, it's in a new window like this. Yeah, I will remember what is that. It's it's a sample of DNA with some gold nanoparticles on microsurface. Okay, that's why it calls gold nanoparticles array, whatever. If also you have an option here to import, but I don't see it. Yeah, I think it's open. If you open once again, here in file types, you can say, okay, Gwyddion automatically detect, and it will do the job. You can ask the Gwyddion to import ASCII file. As I said, 3 columns, X, Y, and Z, and that is your signal. Then you can do it. You can again open it as a raw data file, or as a XYZ data file with a file format XYZ. What is the difference between this and that? Usually, there is almost no difference. This is just ASCII. It's any TXT file. This is a file that should be specially prepared as XYZ. This is any file, because the idea of Gwyddion that you can do whatever you want. X, Y could be coordinates, but it's not necessary to be in micrometers. It can be in ages, it can be in years, months, and so on and so on. So this is more general format. Okay, if we press here a raw data file, if we are not lucky and we cannot see any picture when we select automatically detected, so we go to a raw data file, press again open, and we have such a window where we can say, okay, this is my resolution in pixels. This is my resolution in here it's micrometers. If you have data that you need to calibrate, correct, and so on and so on, you can import as a pixels, and then add you manually add the width, physical dimensions, and then you will see here a picture. I have no idea why it's not working, but it should work like this. Yes, okay, cancel. For example, with this raw file import or ASCII file import, we imported Raman maps customly created, and then we can play with these maps. We can analyze, for example, distribution of the signal, the roughness of this distribution, and so on and so on. So it's really a good tool if you understand how it works, and if you play at home with all this data by yourself, it would be great. Okay, anyway, each time when we open a new file or the same file, it will be opened in a new window, and then you will have a lot of different windows, and you need to understand and to remember where you have what. Okay, let's go further. This I will show you how to make these nice pictures. Yeah, and also since Gwyddion is Linux or Unix based software, so it's a free software, so it's made and it's created on Linux. Then you will have all these problems with Windows, let's say, settings and so on and so on. Like I cannot open just both this window and this window. I need to open one and another one. And when I click suddenly on presentation, everything disappears because it goes on the background. Yeah, sometimes it's not that cool. Так. Okay, so we need to make data processing. So we go to correct data, align rows, for example, and here we are. It's a aligned image. So we have a small artifact here. I have no idea why. Probably it's tried to correct all these big pitches, big DNA molecules, but it failed a bit with the background, but we can cut this part. And then here we have different methods how we can align these rows one with another one. We can do it based on median. So we calculate, for example, 2 or 3 of rows, and then calculate a median one, and then place this median one in the middle. Then next 3 the same, next 3 the same, next 3 the same, and so on and so on. Then we can do a median of differences. Again, we first calculate differences between each 2. So 1, 2, 2, 3, 3, 4, 4, 5, and so on and so on. And then we make a median between them. We can do some, like this. It's another way how to make it. Yeah, we can do like that. Yeah, please, come on. My computer is very slow, as slow as me.
Sorry, Professor, can you show me once again how you open the align row?
Yeah, sure. So you have this window and this window with opened file, the file that I send you, right? And then you go to data process, correct data, and then here you have align rows. Or you can do it a bit differently. You have here align rows. You see, if I keep my mouse on the button, it shows me align rows using various methods. You press the button, oops, and it's here. Because it opens on another screen because I have two screens, okay? But if you press this button, you will get immediately this align rows window. I would really recommend you to follow all this stuff with me, because I will point you just very important aspects. My recommendation to you is to play with this data at home with Gwyddion. So you just try all these methods and try to go. If you really want to know how it works, I mean, in terms of like mathematics and so on and so on, just go to the website of Gwyddion and just read through all of that, all these methods. Because you see there are like 1, 2, 3, 4, 5, 6. There are 8 methods that you can apply to your image. And sometimes it's some of them better than others, sometimes no. Usually, median is the best. Because except maybe this bottom part. This bottom part is not very good, but the rest is cool. Okay, so next one, align rows. We can do it like facet level tilt. We can do it like matching, like polynomial, and so on and so on. You see, you change the method and you change the result. The only thing that you do not change some, let's say, features, the feature differences on your image. For example, you see, I mean, okay, here it will be this image made by median. Yeah, let's make some, I don't know, modus, for example. Okay. And then we have, wait a second. Yeah, we have image like this, and we may compare this image with this image. Here we have differences between 0 and 9 nanometers. And here we have difference between -1 and 6.1. It means if we place here 0, I don't remember how, but okay. If we place here 0, here it will be 7.4 nanometers. So technically speaking, we keep all the features and their sizes, but we change the representation of these. Yeah, okay, let's keep it like this. And also you can see that this image on the back, it's more smoother than this one. I will open one more time the first image. You see, I need to open every time the main window, this window. It's a bit annoying, but at some point you get used to it. There is a button for 3D. Yeah, like this, I think. Yeah, so we press this button, we have the image, and we do see that it's banded. You see, it's bent. So this is exactly what happened when you have raw data. That what I said. It's not exactly like this. It's like this. So it's parabola or semicircle. And also, if we press here the same button, it's like that. So you see, it's flat. So we flatten the surface. We again, by aligning the rows, it also do some flattening. So it changed this curve to more flattened. Yeah, you can see it like this. Yeah, and also if we can compare it with this one. Yeah, so this image and this image, we have all the features around The sizes of the features more or less the same, but it's just different representation. That's all. Yeah, I think this one, and here we also do this one. So you see there is a how to say, there is a special button that calls shift minimum value to 0. It means that before here it was minus 1.3 here, and here it was something else, almost 0, but not 0 exactly. And what this function does, it took this minimal value and says that it's 0. Any IFM, any SPM, I would say. So SPM is what? It's a scanning probe microscopy, not only atomic force, but probe. Probe means Kelvin probe microscopy, magnetic, whatever forces microscopy, and so on and so on. Any of them. You are dealing with a difference. So for example, this is my surface, yeah, this level. And this is something laying on the surface. So I scan first the substrate and then my sample. And what I measure the difference between substrate and my sample. It's not the absolute value, it's a relative value. It's a difference. That's why we can zero it whenever we want. Here or there, because here, you remember here it was minus 1.3, right? And now it's 0. So we just move the scale a bit. Sometimes for IFM, you will need to invert data. What does it mean? It means that, for example, you scan some data, and for example, this BAMP, this microphone, is not the difference is not positive; it's negative, and you need to invert it. It's for some scans, you just need to remember that you can go at any time to data process, well, basic functions, and here you have like this. Yeah, you have invert values. So for many types of IFM, you need to do that. As I explained you, sometimes it depends how you measure. Again, you need to understand very well what you measure, how you measure, and what the result you expect. This is the main maybe problem. As I said, it's a problem, but it's also an opportunity in IFM, because sometimes you have a tip passing by, so like this, the cantilever passing by, like this, like this, like this. But sometimes you have a microphone, your substrate passing by, and your tip is not moving. And for example, for our microscope that we have not the tip going up and down. We have the substrate going up and down. And when there is a substrate going up and down, then you need to invert. But we will see it a bit later when we start working with a practice. Another important tools, a series of tools, I would say. I just need to tack. Another important series of tools is how to measure sizes or distances in atomic force microscopy images. And for that, we have this button that calls extract profiles. So you see, I pointed out my mouse, and there is extract profiles along arbitrary lines. So what we do, we click this button, we have image, we click this button, and then we have these lines. We need to make a line like this. You see, it's written line number 1. So we have some kind of like helices of DNA laying on the surface. And we have a profile. We can measure a bit later. We'll do it. We can measure the width. So it's less than what? Less than something like 30 nanometers. We can measure the height. It's like, well, 2.5 and 4.5. So it's about 2 nanometers. And so on. So we can do another line, for example, like this. If I press Shift, it will be a parallel line. If I don't press Shift, for example, like this, it can be any direction, like this, like that. But if I press Shift, then it will be like that. It will be direct line. So for example, from line 3, we can determine the mean level of our surface. Here it's about like 2.5 nanometer. From line 2 and 1, we can determine height of the object and their width. But in IFM, the better is to work with height, not width, because again, next lecture, Anastasia will explain you. Will explain you some artifacts, and you will see that depending on the sharpness of your tip, you can see very sharp image, or you can see very blur image. So it's not super sharp. Again, you can measure and you can extract profiles. We will do it. We'll do it together, like 2 slides after. Also, you can do the plane correction. Unfortunately, we already done it when we apply this align row. So here it's a plane correction, you see, and there is a plane correct aligning of rows with different methods. As I said, first of all, we need to make height and lateral calibrations. How we do that? We read raw file, yeah, and we know when we will do the first practice, we will do this height and lateral calibration. To do that, we will make imaging of several structures that calls calibration structures. And with these calibration structures, we'll get such an image, and we know the horizontal size, vertical size, and so on and so on. And we know also the image size, kind of like roughly. And we know that, for example, 0.643 volt difference, because we can measure it, and we will measure it, equals to 100 nanometer for the sample of the sample height. Here it's like the test structure that we will be using. Yeah, and what we do, we measure these, as I said before, we measure the baseline, we measure the step size of these testing structures, and we know that the height is like 0.643 volt, and it equals to 10 nanometers, because this 10 nanometers is made on the factory. And like this, we make height and lateral calibration of our images. And of course, we will do several measurements. So here you see an example. This is our calibration sample. Here, it's an example of the pitches. And we make 1, 2, 3, 4 lines. We have different profiles. You can see it here at the bottom. And then we can measure all this picture size, I mean the height and the deep of the well, and so on and so on. So we will do it once we start with the practice. And from that we know how to calibrate all our setup, because we do the calibration of the setup not only for one of the for the other sample. So once we do this calibration, as I showed you, we will be able to make a profiling of DNA of any of your sample, of like Blu-ray. We have Blu-ray samples and so on and so on. We calibrated everything. We do all the stuff, and we start measuring lengths of the samples that we want to measure, like for example DNA. And we draw these lines, and we can measure the thickness or the width or the height of the DNA laying on the mica. One more time slowly. You have this graph, this image, right? And then you go to extract profiles along arbitrary lines, and then you go to this window, okay, that calls profiles window. It appears, and then you draw the line 1, 2, or 3, and then it asking you, what shall I do with all these lines? Shall I interpolate it, masking, graph, and so on? And here we select new graph and then apply. And once we select apply, we will reach this profiles window where we have a graph. We can copy data, and we can change representation style of our lines. And on this graph, we can measure, measure distance like this. We can measure the distance between here and here. And you see, for example, it shows the position of the first line, it shows the position of the second line, it shows the length in nanometers. What I like the most in Gwyddion, that if you keep the mouse on the button, it shows you what this button will do for you. For example, here, there is like measure distance in the graph. Once again, I press, I forgot that I pressed already. This window appear, measure distance in the graph. So you see there are 1 and 2 lines that I already drawn. And for example, if we want to measure the height, okay, wait a second. We can do it like this. So we can place the first line here and the second. So we caring about now this and this. And the difference we got is like 121 and 2 nanometer. The height of the sample. Why I'm selecting the half height of the sample? Simply because this part has already less in the real world. Again, this will be the topic of next lecture, because your cantilever, your needle at the cantilever, tip of the cantilever, it has physical dimensions. It's not dimensionless. It has physical dimensions. And when it approaches to the surface, to the sample, when you're scanning, first you feel the object with a side of the tip, and then you have the feedback. Feedback goes it up and up, and then you start scanning the surface of your like impurity or your sample. And that's why it's a bit sometimes very tricky without knowing the exact shape of the tip and exact parameters of the tip. It's a bit tricky to measure the width, but it's super precise when you're measuring height. And here the same. For example, you can assume that the DNA laying on the mica has the same dimensions in X, for example, and Z. But in Z, we have 1.2 nanometer, and in X, we have 22 nanometer. And this is the difference. Measuring very small objects in AFM, their lateral dimensions, it's a bit tricky and it's not super precise. But measuring the height is super precise, because for heights, we know the position here and we know the position there. That's all. And for lateral dimensions, we know the thickness of the tip, the curvature of the tip, the dimension of the tip, the difference between low and high Z, and so on and so on. There are too many parameters that affecting the width, but too less that affecting the height. That's why we can measure, for example, thickness of one graphene layer or one MXene layer, but we cannot measure very precisely one atom, or let's say clusters, like tens of atoms, because we have very large, because they start the tip will start filling up and approaching this cluster widths like this. It's not exactly in the IFM. In IFM it will be wider, but the thickness or that difference in that direction, it will be really precise, because you point here and you point here, and there is no tip convolution. Oh, convolution is another word. Okay, I hope you understand how to measure distances in graph. Okay, first you need to understand what to do with the image. With image, you do align rows, plane subtraction, and so on and so on. The four main corrections that I mentioned. Then, once you have the good image, you can make 3D image, okay, that I also showed you. Then you need to extract some information like distances, heights, widths, and so on. How to make it? Again, I explained right here, okay? So you make a profile, you extract this profile as a graph, and then on the graph, you can measure whatever you want. You want to measure heights, you measure heights. You want to measure distances or widths, please do it. Then we have 5 minutes, maybe a little bit more, like 5-10 minutes. And I would like to show you that you can measure the roughness of the sample. Sometimes you really need to know the roughness, because based on the roughness, for example, you can determine and you can make materials discriminated. For example, one material is rough and another one is super, like, super flat. And again, here we can do it with a special tool that calls roughness of the sample. I will show you right now. Oh, okay, I will close all unnecessary. We need this image and we need Gwyddion like this. Yes. Here there is a tool. Again, if we press if we don't press, if we just leave a mouse over the button, we have kind of like small tip. What is that? Calculate roughness parameters. So we click it, and then here we can select. We can select. We already have the line, and then based on this line, program automatically calculating roughness, waviness, texture, and so on and so on. But if we select another line, wait a second, example like this. Oh, sorry. Yeah, you can, yeah. So, for example, like this, you see you have different parameters like texture, waviness, and so on and so on. If we move the line here at the bottom, then we have like, again, texture, waviness, and roughness. They are all more or less the same. And texture we have here, like almost nothing. And also we have different roughness parameters. Here roughness parameters is like what? Nothing, like 100 picometers. So we have super flat surface. Yeah, because it's mica, and mica is really flat. And you see here, there are different roughness parameters. I'm not sure that I can make it bigger. Yeah, I can. Yeah, okay, perfect. Like this would be great. So we have roughness average. We have square roughness, mean square roughness, and so on and so on. We have many parameters like this. Yeah. Each of them represents something, and for each application, maybe you would like to have maximum roughness peak height. I know why. Maybe you have small dots, quantum dots, or some catalytic particles, and maybe you want to see this parameter. Maybe you want to have roughness average, or the good one is root mean square roughness. It's more or less the same as a mean square root method. So you create kind of like square root x in this point squared minus x mean squared, and then square root out of that, exactly as mean square root method. And then this is again very small number. It's 100 picometers. It's very small. Again, if you need this roughness, you can say apply, and you can make this texture profiling of your sample. Exactly the same. It's the same story as we did before with profiles. Okay. So again, you can measure something like this, making one, making another one. Here you have some parameters and so on and so on, if you need this. But normally people, when they're talking about roughness, they have they are talking about this roughness average array and RQ, root mean square roughness. Maybe another story, maybe you would like to ask me how to make this colored picture instead of this depressing gray, black, gray, and white. It's very easy. So you click right with right mouse on the scale, and then you have different gradients, whatever you want. For example, you can make it like this. You can make it like that, or like this. It's up to you. You select cold or a little bit fancy colors. This is again, it's sometimes it's important. Or for example, like this, because visualization allows people to understand your picture better. Because I think this one, and you agree with me, better than, for example, that one. This is one is kind of like everything is gray, nothing. And here you understand that this red part is really up than the green part. And then you understand very easily that there is a trench, but as I said, this trench comes from some mathematical treatment of the data. And this trench here at very low Z, but the rest of the sample is located around here, around 2 or 3 and so on. Another tool how to make this colors more visible, I would say. There is a button as it's marked here, you see. Again, if you forget something and you do not know where to get all the ideas and so on, in the presentation, every buttons that I talked today about, they are marked in a red square. Okay, so you open this presentation, it's already on your Moodle, and then you scroll down the presentation and you see all the buttons about what we were talking today. So there is a stretch color range to part of the data. We open it. It looks like that. And then we can play with this. We can select like this. We can select like that. We can select the whole, almost the whole, or like this, or move it, and so on. We can even invert mapping. Take home message that just play with this program as much as you can. Try to get all try to get into every button, at least here on the panel, just to get idea what these buttons are doing with your data and imaging. I think, yes, I explained all this stuff. And then the last one, I think it's an export. For exporting, again, we're using more or less the same interface as everywhere. Yeah, show data browser, yeah, over there. So you see, here we played only with one part of the data, with the height. We doesn't play with phase, with force, and so on. Technically, it's the same, as I said. It's just data that you need to understand what it means, how you get this data and how you can use it. So there is a height, and also what you can do, you can copy, make, delete, whatever. And also you can export TFF, for example, of the data. You see, we colorized the image, and we have here again small icon that show us that it's colorized. We can also export all this texture, profiles, whatever we created, calculated, and we need. Some spectra, if we are talking about spectroscopic data, and so on and so on. So curve maps and so on. This spectra volume XYZ curve map, it's more for hyperspectroscopy. We are playing with images and graphs. And with images, we can say file, save as, we select height, and then we save this as a TIFF file, click, sorry, it's over here. Once you go to file and save as, you will get this window. Here you select TIFF, you select your name of your file, and you click save. Okay, sorry, I have it already exists, so I just need to like this. Click save, export TIFF stuff. Again, I can do some, for example, if I need really good representation of my data, maybe I want to do it like this. Maybe I want to increase some line widths like this, not too much, maybe 6. This one too much again, maybe 10. Yeah, more or less good data, I hope. Yeah, like this. This is already good treated data that you can place for any report. And then you say, okay, and it's saved. I really want you to use this software not only for IFM, but for other 3D data to treat and present it.
С вами был Тибериус. Если видео понравилось, ставьте лайк. Если видео не понравилось, так уж и быть, ставьте дизлайк. Но обязательно напишите почему. Подписывайтесь на канал. Всем пока. До скорого.